Kia ora. Differentiation of trig functions. Firstly, what we want to do is just remind ourselves of some of the trig identities that we have been working with when we looked at the trigonometry topic. So remember, these are on your formula sheet. The first one was sine squared of theta plus cos squared of theta is equivalent to 1. Next one was sine theta is equivalent to cos, in brackets, 90 degrees minus theta. So obviously that's if it's in degrees. And the other equivalent there is that cos theta is equivalent to sine of 90 degrees minus theta. And then we also had that tan of theta is equivalent to sine theta over cos theta. We also looked at the reciprocal trigonometric functions. So we went through this. I'm not going to go into too much depth, but basically we learned about cosec, sec, and cot. So you might want to revise some of that. And what we learned was that if we have sine, cos, and tan, that cot, sec, and cosec are related in this way here. So they're the reciprocals of each other. So that's where we're sitting. So now let's get back to what would the derivative be of trig functions. So if we sketch the curve for y equals sine x, it should look like this. If we then look at the gradient at each of the key points that we have there, what do we see? At x equals 0, just having a look at that gradient, it kind of looks like, and it is, a gradient of 1. At x equals pi over 2, the gradient's 0. At x equals pi, the gradient's negative 1, 3 pi over 2, 0, and at 2 pi, 1 again. If we plot the gradient values that I've just said there, have a look at the function that we get. Hopefully you can identify that as looking like the cos function. So that means we get to say that the gradient curve for y equals sine x is y equals cos x. And a way that I've remembered that is because I used to have a friend called Samira Crossan, and I just always think to myself, S goes to C. It's on your formula sheet, however, it might be something you find a way to be able to remember. Okay, so similarly, if we graph y equals cos x, what you'll find there by doing the same sort of thing is that the gradient function is y equals negative sine x. So again, it's on your formula sheet, but it's one that you end up using quite a lot. Differentiating y equals tan x, we can break it down to sine x over cos x. That means we could use the quotient rule. So just using our quotient rule, which we're already familiar with, what we should find there when we go through that, so we've got f dashed of g minus g dashed of f on the top line and g squared on the bottom line. Then we've simplified, so that's given us cos squared of x plus sine squared of x all over cos squared of x. We can use the trig identity that cos squared of x plus sine squared of x is equivalent to 1. So we have 1 over cos squared of x, which is equivalent to sec squared of x. So in other words, the derivative of tan x is sec squared of x. Again, this is on your formula sheet. So what have we learnt so far? The derivative of sine x is cos x. The derivative of cos x is negative sine x. The derivative of tan x is sec squared of x. Some of the other functions that you can differentiate, on your formula sheet you've got given here the derivative of cot x is negative cosec squared of x. The derivative of sec x is sec x tan x, and the derivative of cosec x is negative cosec x cot x. The key is to know where they are on your formula sheet and how to use them. So, to use the chain rule to differentiate composite trig functions, if we look at this example here, if we had y equals sine squared of x, that is equivalent to sine x all squared. So I've just got here, we treat sine x like it's an x. So that's because we're looking at it like a composite function, or like I've been saying, cover it up with your finger. If we then differentiate around that, then that's going to give us 2 sine x to the power of 1 times by the derivative of what's inside the brackets. So the derivative of sine x is cos x. And so there I've just got multiplied by the derivative of the part you treated like an x. Second example, y equals sine x squared. So in this case, what we're needing to do is to differentiate. So covering up the x squared, differentiate sine, so that's going to give us cos of x squared. Remove our finger and actually look at what's underneath. So inside the brackets, the derivative then is going to be the derivative of x squared is going to be 2x. So multiplying that out at the end. And then you can just rearrange it. So you could say y dashed is 2x cos x squared. All right, so bit of content there, bit of revision. There are 3 exercises. The first one's on page 281, exercise 15.12, and then there's 15.13, and then the final one on page 282 is 15.14. So my thought with those is that probably every second question would do. The middle one isn't very long, so give those a go, and that's where I'll be picking things up from in our next lesson. All right, good luck.